All right. Welcome back again, everybody. Welcome to Modern Mathematical Methods for STEM Majors. I'm Dr. Richardson, and I am excited to introduce you to Chapter 5, which is all going to be about sequences, summations, asymptotic behavior, and the binomial theorem. Let me pull up the slides, and we will get started right away. Right, here we go. So first section of chapter 5 here, let's take a look at an overview of the chapter first. First section is all about sequences. The second section is a cool one. It's all about comparing asymptotic behavior. I'm excited to help you all learn that stuff right there. Section 5.3 is all about summations, a little bit of series. This will help prep you for the end of Calc 1 and then all of Calculus 2. Then we're going to finish the chapter with the binomial theorem. So it's a relatively short chapter. In fact, this is a relatively short section itself, but it's chock full of really important stuff that you're going to use a lot later on. All right, let's look at today's section, section 5.1. We're just going to start with the definition of a sequence, talk about a little bit of notation. We're going to do a whole bunch of examples. There's a lot of examples in this section. We're going to talk about a very special function called the factorial function. Then we're going to talk about recursively defined sequences, and I'll leave you with a helpful resource called the Online Encyclopedia of Integer Sequences. It's basically a free archive of integer sequences. So if you come up with one on your own, you can check to see if it's listed there, and maybe it's not. If it's not, you can submit it to them and they will include it in the archive. All right, so let's start with the definition of a sequence first. The good news is we're well prepared for this. A sequence is just a function whose domain is the positive or the non-negative integers. That's it. So it's really just a function whose domain is the natural numbers. You can think of it like that. So it doesn't fill in the gaps between the natural numbers in regards to inputs, all right? Little bit of notation right off the bat. Instead of writing F1, F2, F3, F4, and so on, typically we write A sub 1, A sub 2, A sub 3, A sub 4, and so on. So you can basically treat these as the same thing. In other words, those A sub things you see, those are the outputs of the function. Those are the list of terms in the sequence itself. So in other words, a sequence is just a list of numbers or elements in a definite order. That's really all it is, a list of things in a very specific order. There's a first term, a second term, a third, a fourth, dot, dot, dot. And you can keep going on forever and ever if you want. All right. So that's really what a sequence is. In this class, we're going to deal almost exclusively with infinite sequences, meaning sequences that go on forever, but sequences can also be finite, so that's all right. Here is the notation that we use for sequences. Let me zoom in a little bit here. Here we go. We use these curly braces like that, just to kind of indicate a set, really, right? Here's A1, A2, A3. The dot, dot, dot means it keeps going on forever. A lot of times we will just denote that as A sub n. A lot of times we'll have a formula for the nth term, which we're going to talk about in a minute. These here, these are basically the starting and stopping index. So here this is indicating that n starts at 1, meaning like there's a first input when n is 1, and then you get a sub 1, which is the first output. And it can go all the way up to infinity, or if it's a finite sequence, you would have a finite number here where the sequence stops, okay? That number n, this is what's called the index of the sequence. It can begin at, well, really whatever number is convenient. Don't feel like it has to start at 1 or 0. It can start wherever you really want it to start. It could even be negative, and you'll see that later on. You definitely see it when you start studying things like Laurent series later on, for those of you that are going to take a complex analysis course. But it's most common to start the sequence at 1 or 0. If it's not specified, like you see right here, there's no starting index specified, then we assume the index starts at 1, okay? At least in this class. A sub n is called the nth term of the sequence. It's the result you get when you plug in n, right? Or it's the one that's, yeah, it's the nth term. I'll just leave it at that. Let's see some examples. So here's a classic example. This sequence right here, the formula for it is n over n plus 1, and it's going to start when n equals 1, and it's going to keep going on to infinity. So here are the terms of the sequence written in ascending order. So when n is 1, you get 1 half. Why is that? Well, you basically take whatever this number is and you substitute it in for every instance of n. So here, a sub 1, it's going to be 1/2 because you take 1 and you substitute it for n. And then you simplify, you get 1/2. There it is. Next step, when n is 2. So now when n is 2, you take n and you replace it with a 2. And then you're left with 2 over 2 plus 1, which simplifies to 2/3. And then you keep going. A sub, oop, that should be a sub. That should not be a superscript. Let me fix that real quick. There we go. That should be a subscript. When n is 3, there you go. You get 3 over 4, and so on, and you can keep going. And one thing I want to point out here, we're going to see it again in a few slides. There's a pattern here, and you want to start practicing recognizing the pattern that you see. So notice like the numerator here is going 1, 2, 3, 4, 5. The denominator is going 2, 3, 4, 5, 6. So there's a definitive pattern to this sequence, and that pattern is given by this formula, okay? Let's do another example. This one is a classic example of an alternating sequence. The terms just follow the form -1 to the n, right? And in this case, n starts at 0. So -1 to the 0 is 1. So the first term is 1. -1 to the 1 is -1. So the second term is 1. -1 squared is 1. -1 times -1 is 1. So the second term there, or term number 2, I should say, or the term associated with n equals 2 is 1. And then it keeps going. 1, -1, 1, -1, 1, -1, on and on and on. All right. Okay, another example. This one, the formula is 1 over 2 to the n. And in this case, notice that the sequence actually starts when n equals 2. So that's going to be the lowest one. When n equals 2, we get 1 over 2 squared, which is 1/4. When n equals 3, we get 1 over 2 cubed, which is 1/8. When n is 4, you get 1 over 2 to the 4th, which is 1 over 16, and so on and so on. So this is just giving you the formula for the sequence. The sequences can be very, I mean, they're just functions, right? So they can be all sorts of interesting structures. They don't have to just be given by a single formula. They can actually be defined piecewise, right? We talked about piecewise functions earlier back in chapter 2. Here's an example of a sequence that is defined in a piecewise way. So this sequence, C sub n, is n when n is even and natural log of n when n is odd. So the formula you're going to use, the rule of this particular function, this sequence, depends on if n is even or not. So since the natural log function can't accept 0 or any negative numbers, let's just start at 1. So the first one is ln of 1, right? Because when n is odd, we do ln. So when n is 1, we get ln of 1. When n is 2, that's an even number, so it's just going to be the number 2. When n is 3, that's going to be odd, so we do ln of 3. When n is 4, that's even, so we just get 4, and so on and so on. So sequences are very flexible, very versatile. They can kind of do whatever you want. They're just a list of numbers that typically follow some kind of pattern, although they don't even have to follow a pattern. They could be totally random. All right? Okay, now we've seen how to generate some sequences from a formula. Here's what I want you to try on your own. I want you to try to go backward. I want to give you this formula, and I want to see if you can come up with, I'm sorry, I want to give you this sequence, and I want to see if you can come up with the formula that would generate this sequence, okay? So just to refresh everybody's memory, remember, think about it for a minute. And then you know what's next. You got to say something out loud to your dog, to your cat, to your hamster, to yourself, to your friend. Just say something out loud to give your brain that feedback to help you process what's going on. All right. And now try to work it out on your own. You're just trying to come up with a formula, something that has n in it, where when you plug in, oh, n equals 1, you get that, n equals 2, you get that, n equals 3, you get that. But you also could choose to start at a different index. You get to make that choice on your own. You do that, and then we'll do it together in a moment. All right. Okay, now let's do it together. I'm going to look for some patterns that I notice. So one pattern that I notice is the numerator here is always a 1. So that's kind of like a fixed property of whatever the formula is going to be. The numerator is always a 1. The denominator looks like powers of 3. This is like 3 to the 1. This is 3 squared, 3 cubed. So I suspect the formula will be 1 over 3 to the n, but what index am I going to start at? That's a good question. Okay, there we go. So I was right in my guess that it's going to be 1 over 3 to the n, or just powers of 3, right? But there's a couple things I want to point out here. With this structure, I had to start at n equals 1, and that's because when n equals 1, you're going to get 1 minus 1 in the exponent, and that's 0. And 3 to the 0 is equal to 1, so 1 over 1 is 1, and we are in fact getting that first term 1, right? But there's another way to express this sequence, another equivalent way to express it, and that is 1 over 3 to the n, but you got to start when n equals 0. So when n equals 0, you get 1 over 3 to the 0, which is 1 over 1, which is 1, and so on. Before I get to this important note at the bottom here, one tip that I want to give you all is whenever you come up with a formula for a sequence, test it out. Plug in a couple of numbers to be sure that it is actually going to work. We're going to do that. Where is it? Where is it? We're going to do that in a few minutes here when the sequences get a little more complicated, but just test it out. So plug in n equals 1, n equals 2, n equals 3, and just see if that's actually producing the terms that you see written out in the sequence, right? If it's not, then you need to fix your formula. You need to massage it, change a detail or two, but it should be exactly this sequence when you plug in n equals 0, 1, 2, and so on. All right. Now, to this note here, this is an important skill. You're going to get some practice with this on the homework too. This technique that you're seeing going from here to here is what's called an index shift. It's an index shift because we're basically shifting the index, in this case, by 1 unit. It can be really useful because it can change the structure of your formula and it can make it cleaner and it can make it more revealing about the structure of things. I actually feel like this is a better formula for this sequence because my original thought was these are powers of 3, right? And this actually shows that they are just straight powers of 3 for n equals 0, 1, 2, 3, and so on. All right. The important thing about an index shift is that even though the index changes, the terms of the sequence do not change. So if you plug in n equals 1, n equals 2, n equals 3, you will get this sequence. And over here, if you plug in n equals 0, n equals 1, n equals 2, you will still get this sequence. So even though the index has changed, the starting index has changed, the sequence itself is unaffected. All right, that's an index shift. Okay, here, let's do another one. And again, I want you to try this one on your own. Here is a sequence, and I want you to try to find a formula for it. All right, so think about it for a minute, stare at it. Now, say something out loud, maybe something you notice, a pattern, and then try to write it out. So try to come up with a formula for the sequence, and then test a couple of values of n and see if it actually produces the sequence that you see here. All right, now let's take a look at it together. The main thing that I notice about these is they're all odd numbers. They're literally this is the list of odd numbers, 1, 3, 5, 7, 9, 11, 13. I can even say what's going to come up next, right? So we know the structure of every odd number. Every odd number is going to look like 2n plus 1 or 2n minus 1. It just kind of depends where we want to start. So indeed, those are two equivalent representations of this sequence. I called it B sub n. So you could make it 2n minus 1 if you want to start when n is 1, or you could make it 2n plus 1 if you want to start when n equals 0. And again, plug in some values of n to see if it actually works, right? So if n is 1 here, we get 2 minus 1, which is 1, check. When n equals 2, we get 4 minus 1, which is 3, check. If n equals 2, we get, I'm sorry, if n equals 3, we get 6 minus 1, which is 5, check, and so on. Now let's look at the other version. The other version will produce the same results. If n equals 0, we get 0 plus 1, which is 1. If n equals 1, we get 2 plus 1, which is 3. Check. And so on and so on. So that is the correct formula. Either of these are the correct formula as long as we take note of the starting index. All right. So that sequence that you just saw, this one right here, this is actually an example of what we call an arithmetic sequence. These are a particular kind of sequence that are pretty important. An arithmetic sequence is one that starts at a given value, and the consecutive terms are determined by a common difference D. This might sound familiar. The formula for an arithmetic sequence will always have this general structure. So the nth term is going to be the first term plus d times n minus 1. And the reason that this is a handy formula is because, let's say you wanted to know the 50th term of that sequence. Well, you don't need to just count up and like do that 50 times. You can just use this formula. You just need to know the first term. You need to know the common difference. And then if n is 50, you would just do 50 minus 1, which is 49, multiply, and then add the results. So that's it. Now, this should sound a little bit familiar, this notion of a common difference, right? The common difference here. These functions, arithmetic sequences, are actually linear functions, and they're just defined on the natural numbers. That's it. The slope is d, and the initial value is a1. So what I'm really trying to say here is arithmetic sequences are just linear functions. That's it. The only difference between these and what we saw earlier in the course is these functions are only defined on the non-negative integers, like the natural numbers, 1, 2, 3, 4. They're basically discrete linear functions instead of continuous linear functions. The linear functions we explored before, you could basically draw them by keeping the pencil on the paper, right? Well, not the case with a sequence. Sequences are discrete, so it's just a bunch of points, like dit, 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 like so, as opposed to a continuous function like that. Um, you might have trouble seeing the linear structure here, but take a look at this. If we instead decided to start our index at 0, look at what happens. We're going to perform an index shift. And what we get is that a sub n is actually the initial term plus d times n. And this is exactly the slope-intercept form of a line, right? Here is the initial value, the y-intercept. Here is the slope, d, and n is our variable. So arithmetic sequences are linear functions. That's it. Okay, another cool result. If you remember, what was the characterization of a linear function? Remember, it was that the consecutive outputs had to have a common difference, where if you took the next term and subtracted it from the previous term, you would always get the same number, and that number was the slope. Well, check out this calculation. Let's just look at the difference between two consecutive terms of this sequence, a sub n and a sub n minus 1. So here is the formula. And here's the formula when the index is n minus 1. So here we replaced n with n minus 1. And we're just going to do some arithmetic. Pun intended, I suppose. We're just going to do some arithmetic. Here, we're going to distribute this negative to these terms and simplify what's going on in these parentheses. So you're going to get negative a1, negative d times n minus 1 is n minus 2. Now, the A1 terms cancel. There's an A1 term here and its opposite, so they cancel. Next thing I'm going to do is I'm going to distribute the D's here. So distribute the D to those two terms, distribute negative D to those two terms, and we're left with dn minus D and negative dn plus 2D, which is what you see right there. The dn's cancel. So here's a positive one, here's its opposite. They cancel. And then we're left with negative d plus 2d, which is just d. So in other words, the difference between consecutive outputs is a constant, and it is that number d. That's the common difference, all right? Pretty cool stuff, huh? Literally showing up the characterization of a linear function. Okay, now, let's pick a sequence that's a little bit trickier. I want you to try this one on your own, but you may have to combine some techniques to get this one, all right? So take a look at this sequence. It's 1, negative a half, 1/3, negative a fourth, 1/5. All right, and just think about it for a minute. All right. Now, give your brain some verbal feedback. Say something out loud, something you notice about that sequence. All right. And now try to find a formula for it. A closed formula. You get to choose the starting index. Go for it. All right. Here we go. Again, this is where the math gets kind of creative. So I think it's actually kind of fun. And remember, there's no risk. So if you feel overwhelmed, just take a deep breath and let that anxiety disappear. All right. We control the numbers, they don't control us. Just follow your nose, break things into little pieces. Nobody is expecting you to just know the formula outright instantaneously. Look at the pieces and look for patterns, okay? One thing I notice right away, the numerator is always 1. That's a good place to start. So I might start with this. Numerator is always 1. The denominator looks like it's just the positive integers. Here, this is 2, 3, 4, 5. I could think of this as 1 over 1. So I believe the denominator is just going to be n, and that would be the general form. Now, there's one other detail I notice here, and it's that this sequence has an alternating sign. Notice that the first term is positive, and then negative, positive, negative, positive. So I need to get some kind of alternation here. And we actually saw this in a previous sequence when we had that -1 to the n, right? So let me try that. Maybe it's -1 to the n. Maybe that's the formula. Now, where do we start? What are we going to start with? Let me put the little braces here. Ooh, I can do better than that. Come on. That's a little better. Um, well, I can't start with n equals 0, that's for sure, because if n is 0, then I'm dividing by 0. Oops, hold on one second. I just moved my. Hey, come here. Get back there. If n is 0, then we're dividing by 0, and I don't see does not exist or undefined as the first term. So maybe we got to start at 1. So maybe n starts at 1, and the dot 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 that you see here means it keeps going to infinity. So this is a good guess. Let's check to see if it's right. Let's check real quick. Okay, if n is 1, then the denominator is 1. -1 to the 1 is -1. Ooh, that's not right. Okay, let me check the next one. What if n is 2? If n is 2, then we get a 2 down here. -1 squared is +1, so this would be +1/2. Oh, okay, that's not right. But the good news is it looks like the size of the terms is correct, but we have the sign off. So what we need to do is we need to change this exponent to one that's more accommodating. Maybe I'll just do a +1. There we go. Now everything should line up the way it's supposed to. So when n is 1, we get a 1 down here. 1 plus 1 is 2. -1 squared is 1. So we should have +1 for the first term. Check. Okay, now let's do n equals 2. We get a 2 down here. 2 plus 1 is 3. -1 cubed is -1. So we get -1/2. Check. Okay, that'll work. This is a formula for it. That's a formula for it. Let's see the next slide. Oh, there we go. All right, so check this out. Let me actually pull this up here too. Um, Here I actually did the check. So I'm going through and I'm doing the check to be sure it's valid, but I want to point something out. Let me zoom in right here. Notice that in the formula I had written down working through it on my own, this was an n plus 1. But that's okay. There's lots of ways to write these formulas that end up being equivalent. You just got to make sure they actually give you the same terms. This will give you the same terms. So here, if I did n minus 1 for the first term of the exponent, I would have 1 minus 1, which is 0. -1 to the 0 is 1, so we're good. And then here, if n is 2, we get 2 minus 1, which is 1, right? -1 to the 1 is -1, so we get -1/2. Check, and so on. So there's a lot of flexibility with these things. You just got to check your work, all right? Check your work. Be sure the pattern that you came up with or the formula you came up with is actually matching the sequence that's given. All right. Um, Yes. Okay, so a little specific here. This factor right here that you see, this -1 to the n minus 1, or to the n, or to the n plus 1, that is actually what we call an alternating factor. All right. And this alternating factor is what produces the alternation in the signs of the terms. So whenever you see an alternating sequence that's going from positive to negative, positive, negative, positive, negative, or it goes negative, positive, negative, positive, negative, positive, and so on. What you're going to need is you're going to need an alternating factor of some form. It might be -1 to the n, it might be -1 to the n plus 1, but if you see that alternation, you will need an alternating factor in your formula, okay? This is a classic one. There is another common alternating factor. It is cosine of n pi. We'll talk about that later on. I think it might show up. I don't think it shows up in the activity, but when we talk about the cosine function in chapter 6, we'll talk about cosine of n pi. All right. Okay. Now, there's a bunch of good examples. Now we need to talk about a very special function called the factorial function. This function shows up all over in mathematics. It shows up a lot in statistics, probability, that type of stuff. It actually shows up a lot in my own research in fractal geometry. So it shows up quite a lot. But here is what it is. Given a non-negative integer n, the function n exclamation point is called the factorial function, and it is defined in this way. N factorial, that's how we pronounce it. So when you see that exclamation point, it's not like n, it's n factorial. Okay, kind of a good math joke there. So how do we define it? N factorial is the product of all of the integers that are less than, I'm sorry, the positive integers that are less than or equal to n. So n times n minus 1, the integer just below, times n minus 2, the integer below that, times n minus 3, the integer below that, and you keep multiplying all the way down to 1, all right? A little note here, I won't dwell on it too long, but 0 factorial is actually well defined, and we define it to be 1. Uh, why that's the case, maybe we can talk about it in class. I guess the the short answer would be because that's the value of the gamma function when it's 0. But we won't worry about that. There's a lot of heuristics that show that it should be defined to be 1, but we can talk about that another time. You can just take this as a given that 0 factorial is equal to 1, and maybe we can talk about it in class. All right, so let's see some examples. That's a pretty general definition, but here's a concrete example, a couple of them. 7 factorial is literally 7 times 6 times 5 times 4 times 3 times 2 times 1, and when you multiply all those together, you get 5040. Yeah. All right. 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And that ends up being 3,628,800. All right. Here are the first several terms of the factorial sequence, where we're just letting n start at 1, and then we're doing 1 factorial, 2 factorial, 3 factorial. You get 1, 2, 6, 24, 120, 720, 5,040, 40,320. So one thing you want to notice is that the factorial function grows very quickly. By the time n is equal to 8, you're already at 40,000. So this is another function, kind of like an exponential function, where it just explodes in size very, very quickly. We're actually going to explore that phenomenon in the next section when we compare asymptotic behavior. Really just looking at how these different functions grow and which ones grow faster than the others, and getting kind of an order relationship of growth, okay? That's the next section, building up to that. All right, so another cool thing about the factorial function is it admits a very important recurrence relation. So let me start by defining that. What is a recurrence relation? It's basically an equation according to which the nth term of a sequence is equal to some combination of the previous terms. In other words, what we're saying is to get the next term, you combine some of the previous terms in some way, and that way is given by some equation where you're like, oh, okay, to get the next term, do this to the previous terms, and that will give you the next term that follows, okay? So for the factorial function, it has a really, really nice recurrence relation, and it's this right here. N factorial is equal to n times n minus 1 factorial. And this actually gets used a lot when factorials are involved because it lets you simplify things. Let me go back a slide for a second. Let's take a look at 7 factorial again. Notice here that when we expand 7 factorial, we get 7 times 6 times 5 times 4 times 3 times 2 times 1. Well, check this out. This piece of it is 6 factorial. So really what we can say is 7 factorial is equal to 7 times 6 factorial. That's the recurrence relation manifesting in the expanded form right there. So this is really handy because a lot of times, especially when you're working with permutations and combinations, we'll see that in the binomial theorem, you can cancel a lot of these factors because of this recurrence relationship. All right. But that's what it is right there. We could even do here, like look at this one, 10. This piece right here, this is 9 factorial. So we can write 10 factorial is equal to 10 times 9 factorial. And we could even do more than that. We could even peel off more factors if we need to or if we want to. Let me give you an example up here with 7 factorial again. Like take a look at this right here. This is 4 factorial. So we could write 7 factorial as 7 times 6 times 5 times 4 factorial. Pretty cool stuff. It's just a nice way to rewrite these factorials using that important recurrence relation. This one right here. So this is definitely one that you want to memorize, and you won't even really need to memorize it. You're just going to get comfortable using it with enough practice. All right. Some cool things about the factorial function. For one, it can actually be extended even to the complex numbers, and thus the real numbers, in a natural way. And that extension is what is called the gamma function. If you would like to read about it, I encourage you to. It's right there. You can follow that and read about it on Wikipedia. The gamma function is basically a generalization of the factorial function. And the reason we call it a generalization is because this function, which is defined on all complex numbers, agrees with the factorial function on the positive integers. Meaning, the factorial function gives you a sequence, right? It's basically you plug in 1, you get a number, you plug in 2, you get a number, you plug in 3, you get a number. That'll give you a discrete sequence. But if you wanted to know, like, what is 1.5 factorial or what's pi factorial, we can define that in a natural way, but it's a little bit too advanced for this class. You need to know about integrals if you want to define the gamma function. So I'll let you go down that rabbit hole on your own if you would like, or we can talk about it later on in calculus too. All right. Um, Little Mathematica tip here. Mathematica also knows the factorial function. It recognizes the exclamation point as the factorial function. So if you wanted to compute 20 factorial, you can just go to Mathematica and type 20 exclamation point, and it'll calculate that for you. Or you can just call the function itself factorial and then put the number inside the argument there. All right. Okay, now let's talk about recursively defined sequences or just recursive sequences. So a recursive sequence is a sequence that has a finite number of given initial terms, and the remaining terms are generated by a recurrence relation, just relating the previous terms. So this is what a recursive sequence is. You are given a couple or a few or one initial term, and then the next term is determined by how you want to combine those previous terms. All right. So let's do an example. All right. And I want you to try this one on your own, but let me explain it. I want you to write down the first 5 terms of this sequence, which is defined recursively. Let me explain it a bit. So here's what it's doing. F1, the first term is 1. F2, the second term is also 1. Then, if you want to produce the nth term, you add up the previous 2 terms. That's what this is saying. So if you wanted to give you a little hint, if you wanted to find F3, you would add up F1 plus F2. Okay? So I'll leave it at that. I don't want to give too much away here, but I do want you to try this one on your own. so you can ponder it for a second. All right. Then say something out loud, maybe what you notice, or maybe you already know what the third term is going to be. Right? And now try to write it out. Try to write out the first five terms. So you should have all the way up to F5, or you can go further if you want. Right, here we go. So here's how we're going to get the first five terms. We're actually given the first two. F1 is 1, F2 is 1, F3 is adding F1 and F2. 1 plus 1 is 2. F4 is adding the previous two terms there. So it's F2 plus F3, which is 1 plus 2, which is 3. F5 is going to be adding the previous two terms, F3 and F4. So you get 2 plus 3, which is 5. And you could keep going. Now maybe you can see the pattern. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 8 plus 5 is 13. And you can keep going and going and going. Now, maybe some of you have actually seen that pattern before. These are what are called the Fibonacci numbers, and that is the Fibonacci sequence. 1, 1, 2, 3, 5, 8, and so on and so on. Those are the Fibonacci numbers. Again, you can read up about those. They are very popular. They're a common sequence. It shows up a lot in nature, which is kind of interesting. The structure of the Fibonacci numbers shows up a lot in nature. Why that's the case? Well, you be the judge. You be the judge. Okay, let's do another recursive sequence. I want you to try this one as well. We're going to let A and R be real numbers, so just real numbers. Write down the first five terms of this recursively defined sequence. So A1 is A, and AN is going to be the previous term times R. Okay, so give the first five terms of that sequence. Think about it for a moment. Okay, say something out loud to yourself or to your cat or your dog. And now work it out. Write out the first five terms of that sequence, and we'll do it together in just a moment. Okay, here we go. All right, well, we're already given the first term. The first term is A. The second term is going to be this first term times R, so we get AR. The third term is going to be this one times R, so we get AR squared. And then we'll get AR cubed, we'll get AR to the fourth, and so on and so on. In general, we have this pattern right here. The sequence is A times R to the n minus 1, if you want to start with n equals 1. Or if you want to start at 0, it's just A times R to the n. All right? Maybe that structure looks a little bit familiar. Number times number raised to a power. Well, this type of sequence is what we call a geometric sequence, and it's critically important in Calculus 2 and beyond. They show up a lot in my own research as well. And geometric sequences are just exponential functions. That's it. They have the same structure as an exponential function. The only difference is that these exponential functions are defined on the natural numbers. So they're discrete. They're not continuous like those exponential functions that we explored back in chapter 4. They're more like dit, 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 like so. So they still have the structure of an exponential function, but they're not continuous. They're not defined on the real numbers. They're just defined on n or the non-negative integers or something like that. Here, the initial value is a. We call it the initial term in this case. And r is actually what we call the common ratio in this case. All right. So, oh yeah, since I'm mentioning the common ratio, there's a recurrence relationship here, right? This was a recursively defined sequence. And what does this relationship mean? In other words, it means that consecutive terms are proportional. They're proportional to each other, and the constant of proportionality is r. So here you have that characterization of an exponential function showing up again, right? an divided by an minus 1 is r, and that's the common ratio characterization of an exponential function. Cool, huh? So you've got arithmetic sequences, which are linear functions, and you've got geometric sequences, which are exponential functions. That's the basic idea. All right, one last thing, I'll leave you with this. There is this really cool resource online called the Online Encyclopedia of Integer Sequences. Last I checked, they have over 360,000 integer sequences. So if you come up with one or you want to see if there is a formula for one, check out this website. You can literally, if you come up with like a pattern where you're like 2, 5, 8, 13, 1, you can plug those numbers in to the prompt on the OEIS, and it'll tell you if anybody has submitted that sequence and come up with a closed form or a recursive form, and it will give you tons of information about that sequence. So check it out. It's really fun. I had to use it for my own research because I had to see if there were closed forms for some patterns that I was exploring. It turned out that there were for some of them, and that for other patterns I had noticed the sequence was not listed on the OEIS. So anyway, check it out when you get a chance. But on that note, let's play. All right, that's it for sequences. You'll get tons of practice with them the more the chapter goes on. Um, don't really have too much more to say, so I'll just say thank you all again, and I will see you in the next section where we talk about comparing asymptotic behavior, and that's a fun section. All right, take care, everybody. See you next time. Thanks for watching.